All right, so welcome everybody. I'm really happy that we're going to start a series of readings. It should take about 4 readings in total, 4 weeks to get through this this essay written in 1935 by Max Planck, the great physicist. But he's so much more than that as well, and I'm going to say a few words about Max Planck per se and some of the historical dynamics and epistemological battles that he was fighting that sets the context for this essay, since this essay was written in 1935. I mentioned in my introduction email that Max Planck, unlike many other people of German descent, chose to stay in Germany as a scientist, and he's criticized for that. People say, well, Albert Einstein left and other scientists left Germany as Nazism was on the rise. Why did he stay behind? Was he sympathetic, to the Nazi cause? And no, not at all. When you look at his life, he lived a long life. He lived from like the 1850s until 1947. He was devoutly anti-fascist. He was a defender of the greatest classical traditions of German science, of German art, of German music, which was something that Hitler really despised. Max Planck was not a Nietzsche Wagner German. He was a Schiller German and a Kepler German and a Cusa German. He speaks of all of these characters as far as they relate to his own soul, his own development and identity throughout his life. I'm going to read a little excerpt from one of his references to Kepler in about 12 minutes. But he really wanted to defend what was good and universal about the German culture against the rise of Nazism and also Nazi science policy that was coming in an ugly way with eugenics, right? The science of racial purification, a very deterministic idea of, imposing your will onto the system that you want to scientifically manage with somewhat Nietzschean arbitrary ideas of will to power, that right is based upon he who has the strength to impose his will onto the weaker. And that doesn't make for good science. But on the other hand, there was a reaction against a lot of this determinism, this genetic determinism and stuff that was coming around. And also we saw a lot of this determinism in the Bertrand Russell circles as well, who were promoting things like the Principia Mathematica, who were trying to say that, if we only had enough data, we could reduce all of the universe, all of space-time can be reduced to a limited series of axioms that you could deductively and inductively just, bring and describe everything around. And with this very, systems analysis type of theory that they laid out in 1910, and it was a very influential thesis. They said that you could, go back in time to figure out what was the start of everything. You could know everything that was ever going to be, all the way to some assumed heat death of the universe. And Bertrand Russell and those who followed him, who followed that theory, like Norbert Wiener, John von Neumann, a lot of the systems analysis crowd that formed the basis for a lot of the language that has come to be used by a lot of the technocrats running today's, or trying to manage today's world with great resets and other things. They're all using this language. They all believed in this idea of a deterministic view. So on the one hand, you had that. On the other hand, you had a reaction against that unnatural way of thinking, because it's pretty offensive and it pretty much destroys your idea of free will, right? The idea of freedom per se has really no meaningful existence if you believe that. The idea of creativity really has no meaning either if everything is, predetermined, right? What does creativity mean? So the reaction against that was found amongst a young group of statisticians who believed in the gambling theory of the universe, that really truth does not only is truth not deterministic, but it doesn't even exist. It's not even knowable. It's in no way accessible to the mind of human beings. And the universe is fundamentally ordered by random behavior. And you saw this being expressed in people who were applying this to random mutations in biology, causing what seems to be ordered, measurable things in evolution and the evolution of species. They're like, okay, it's ultimately just random mutations in the small that are beyond reason that cause these macro things to happen. Or you saw it as well in people who were even looking at dead physics, just the behavior of electrons, protons in the nuclei. I just lost my camera, I'm sorry. Let me just see if I can fix that. Okay, that wasn't so bad. All right. So just to, I want to do a little bit of a screen share here. Share screen.
And let's open up this thing. There's about 8 slides I put together. So now Max Planck. So Max Planck enters, and he's doing battle with both extremes. The random folks, who are known as the Copenhagen interpretation, the school of thought that arose with a lot of Rockefeller funding, actually, around Niels Bohr, Max Heisenberg, and what was called the Copenhagen School. And then the other, as I mentioned, the determinists. And Max Planck was saying, look, I made discoveries, very important discoveries, and people who I'm friends with and work with did similar paradigm shifting discoveries. He was close friends and even a musical companion with Einstein and many other great scientists, Dirac as well. We don't think in either way. We're not of either school. And he was trying to intervene on that process, as we will see in this philosophical treatise. So I mentioned in some of the opening remarks, I mentioned Kepler. Might as well just make this a slideshow. So Kepler is the handsome gentleman here who developed 3 laws of planetary motion. We were introduced to some of these in the previous readings over the last few weeks over the science of Christian economy, but not in depth. That's why I was mentioning that if anybody is able to buy his book on the harmonies of the worlds, published in 1620, they should. Kepler's model of the solar system is not what you'd expect. What you see here is actually, in short, Kepler's model of the solar system. This is where he developed his 3rd law, which was the law of, well, here's the 3 laws that I just found is a quick demonstration. Oh, geez. Sorry. Okay. So the 3 laws that we see are one, that planets move in ellipses. So he's the guy who discovered that it's not circles, but it's actually ellipses that planets move in. That idea that broke the world's mind, the mind of everybody, free of the belief in circles and these imaginary mathematical points called equants, which formerly had dominated for thousands of years of astronomy. You had to believe in this. He liberated people's minds in order to understand that, no, there's actually ellipses. That gave all of a sudden an idea of quantization to each planet, because if each planet's ellipse is different, but they're all ellipses, then that means each planet has a minimum and a maximum. It has a quickest and a slowest. It has a nearest and a furthest position. That gives your mind a whole different array of tools to play with when you're thinking about what are the causal laws organizing why the planets are where they are and not some other place. Most people didn't think you could even know that. They just said all you have to do is describe it mathematically, build a model, let it run. And if it comes close to your observations, that's just fine. That's enough. Kepler said no. And he was uncompromising in that and made a lot of enemies for that as well. His 2nd law was a derivative of the 1st, where he was able to demonstrate, as we see in figure 2, that any 2 similar times that a planet moves around the perimeter of an orbit, in this case, they're giving the example of 6 months on one side, 6 months on the other side. So that's probably not the Earth orbit that they're using as an example, probably Mars. Then the area swept out will be identical. So there's a constant there. Whether you're looking at Jupiter or Saturn or Mars or Earth or Mercury, you will have a relative constant. Now we've discovered that this is not an absolute. There's slight, as our measuring tools enhanced in over the years, we've discovered that there's slight divergences, but this is a really sharp constant that he discovered. The 3rd constant is his famous cubic. The cube of the mean distance of every planet to the sun has a relationship to the square of the periodicity of each planet as a whole on its orbit. So basically, you got to imagine a square and a cube. It's basically, that's how he's thinking about it. Don't get boggled down by the mathematics necessarily. The math is important, but really there's a 2-dimensional, 3-dimensional function, a relationship of volume and area. And that when you take the volume of each planet's mean distance from the sun, then you get a relationship to the square of its full orbit, one period. That is that 3rd law, which was his most cherished, the one that he prized the most, because all of the other laws were done so that he could build as a means towards the end of discovering why his theory that he had since childhood and that he discovered by reading Plato's Timaeus, that he wanted to prove that God created the universe in a harmonic, intelligible, creative way, which Plato lays out in the Timaeus. That was his really life's mission. And he did this with political views in mind, because he was a weak man. He couldn't join the military. He didn't want to join the military, right? His dad died in the military as a mercenary in Germany. It was the 30 Years' War that was waging. Half of Germany died. So there was just chaos. Most people only had a very negative view of the universe and of man, based on the fact that, you know, death was a normal thing. Everybody, right? I mean, it's hard to put yourself in the world that they lived in Germany at that time. So that was Kepler's way of intervening into that process, was by demonstrating that, no, there is a higher harmonic law that transcends the seeming chaos of our senses. And it's by knowing that we can inform our statecraft, our ability to judge laws and make better laws that are in harmony with God's law. And he's very clear on that when you read his writings on the harmonies, which he dedicates to the King of England, King James, hoping that he repents and becomes a better man. Also, Schiller's Wallenstein trilogy drama is important, because Wallenstein was a patron of Kepler, a general of the 30 Years' War who used Kepler in Kepler's forecasts. He passed himself off as a bit of an astronomer, but had, I think, a deeper geopolitical insight of what was going on, such that he was such a successful forecaster of what the general should or shouldn't do, which resulted in the general in Wallenstein winning some miraculous battles. So on the left-hand side, there's an image of an important way which one could demonstrate the planetary system as a system, featuring the famous, cross sections of a cone, which we saw in the previous week's readings, where you could get ellipses by making cuts on a cone that are not perpendicular to the base. So anytime you cut at a bit of an angle towards the vertices, and you cut across the cone, you get ellipses of different eccentricities, right? The foci are going to be in slightly different locations depending upon where you chose to make the cut. And if you could project those, you could basically express each planetary orbit on a cone like that. So Mercury being at a high eccentricity would have a deeper angle of cut, whereas Venus would be closer to a circle. It would be a very minimal degree of cut. You could do those things and then project it onto a plane of some sort and demonstrate your entire solar system that way. You could also find golden section and harmonic relationships that way too, which is what Kepler did. And this is what LaRouche, in the writings that we were reading previously, was making a point that if you want to understand physical economy and statecraft, you have to have a proper education system that gives kids the experience mentally to go through that understanding that that's the nature of the space-time that we're born into. Also, parabolic curves, hyperbolas that we find in comets and other planetary bodies are also expressible by cuts from or sections from the cones. So what are we dealing with? Max Planck is famous for making a penetrating discovery into the nature of light and matter. Up until really Planck's discovery, light was understood principally to be a wave, something which moves in spherical waves, right? So you have a light source like a candle. As you move away from the candle, the viewers at all angles around it in a sphere will be able will receive the light from the candle to their eye as they move away from it at the inverse square law. So the same principle of gravity, the gravitational effect of the inverse square, is something which we also find applied to the intensity of light's diminution as it hits a point of observer, right? One of the things that people like Huygens worked on and discovered, who was a teacher of Leibniz, who converted him away from the Cartesian school. Leibniz was a defender of Kepler and who really took Kepler's challenge to future mathematicians to discover a language that could measure infinite rates of change, which Kepler could not do. So Leibniz, 50, 60 years after Kepler dies, takes up the challenge and discovers the calculus. Anybody who believes that Isaac Newton was the discoverer of either the calculus or his work on or in gravity even just simply hasn't read Leibniz or Kepler properly to discover who actually who are the people who made these breakthroughs and who is Newton plagiarizing. So all that to say, Huygens is the guy who recruits Leibniz, and he does amazing work on optics and on light, along with Fermat. And he discovers, it's been observed, but he makes breakthroughs on the nature that light, there's certain minimum maximum principles of light's behavior as it moves through different mediums, and you have different angles as it goes from one medium to another. That's what Fermat made it as a discovery, which became known as the economy of nature principle of light of least action, that light chooses the path of all possible infinite paths it could choose when it moves from like air to water, the path of least resistance or least action. You also discovered that there was interference as it became understood as being a spherical wave, as they created conditions where they moved a light source through two different slits, that the light sources coming out of either slit, in this case we have S1 and S2, would interfere with each other, or at some points amplify each other, such that when they hit a flat surface, you would get these shadows and light, shadow and light, these minimum maximum points on, which you see here on the right. That's an illustration of that effect. So it was understood to be a wave. However, Max Planck did some work, which I'm not going to go through, but there are some incredible documentaries and videos going through his discovery, which he was looking at the light distribution curves as they are emitted by Bunsen burners. So different chemicals emit different types of light and different spectra. However, the intensity of the light, of the energy input, will always cause a certain distribution curve of radiations coming out of whatever you're heating up, whether it's calcium or phosphorus or whatever. And so nobody could figure out why is the distribution of what's being emitted by these different black body sources what we see and not something else. Why do we find a certain constant continuum? And we've seen these examples. Oh, can't see my face. Anyway, so he was putting his mind to that. One of the consequences of his work is that light, it's not so easy to say that it's only a wave because it interacts with this newly discovered phenomenon called electrons. So electrons being something which had only recently become discovered as part of what makes up matter. This is the beginning of the atomic age. And one of the paradoxical things, and I'm realizing here that the image that I selected is wrong. Somebody who made this image actually made a mistake. I'm reading what they're saying, where they say here on the left that you have the ultraviolet, the purple lights, where they say the incident, I can't read it, the incident light's frequency is less than the threshold frequency, and we see no emissions of photoelectrons from, let's say, a silicon or metal plate, for example. When you put a light of ultraviolet frequency onto a metal plate, they're saying it's not going to cause a motion of electrons. Whereas when you have low energy incident light coming onto the plate, you get a little bit of electron motion, right? They're hitting kinetically and causing the motion of electrons. And then you get a lot of electrons moving with what they say is high energy incident light, which is red. The mistake that they're making is that they mixed up the red and the purple. It's actually purple, which is higher energy than red. Red is lower energy. So the results would be, you got to flip it in your mind, right? Everything is right, but the thing that would cause this motion is the high energy ultraviolet light causing the motion, or even more motion of electrons in X-rays, but not with red lights or infrared lights. No, it's fine. So yeah, just keep that in mind. The one thing that Planck discovered in looking at his constant, in discovering and working through his constant, is that there is a certain discreteness, that even though you can increase the intensity, the energy input of various light sources, they will not cause, like that red light, you can increase the intensity of the red light, but it will not cause any motion of electrons. There are, however, as you increase the intensity and move it into becoming yellow and then white and then bluish and then ultraviolet, it moves electrons at a certain rate. It causes the motion of electrons. However, it doesn't happen in a continuous fashion. What happens is you can increase it from, let's say, 50 to 100, and it will cause a certain amount of electron effect. All of a sudden, after 100, you just go to 100, and whether it's 51, 52, 53, it'll still have the same effect. 70, 73, 74, 75. I'm using an example here. I'm using an arbitrary number, but it'll have the same effect. It will only cause the same amount of effect of electron motion. But all of a sudden you get to 101, and all of a sudden you're going to get a completely different higher density array of electron motion in your effects when you shine that light onto a photoelectric plate, or onto a metal plate. So you could almost say, as an example, you can imagine putting energy into pushing a child on a swing, right? And you're putting energy, and you're putting a little bit more energy in, but that kid is still only moving up 1 meter. And you're putting more energy in to your push, and that kid is only moving up 1 meter. And then all of a sudden, a certain threshold is passed, and you're now putting a lot more energy in, and now all of a sudden, the kid moves up 2 meters. So that's sort of the type of thing you can keep in mind, is what's happening. So all of a sudden, we see that there's a quantized, discrete nature to light as it relates to matter, and that also relates to heat. And there's a penetrating power of light, which is related to also heat and vibration. So you're dealing with an intersection of a bunch of what formerly were thought to be separate phenomenon that we're coming into realization are all parts of the same thing. There's a battleless wage when people are now trying to figure out, how do you read into this? How do you make sense of this strange phenomenon? And, you know, things like an X-ray wave could cause a certain electron to be emitted from one plate, and then if that electron now emitted hits another plate, it can collapse and then and cause a wavelength, an X-ray wave of the similar frequency, to be emitted by the second plate that it causes. All of these things are very paradoxical. They completely defy the laws of known classical physics as far as they are popularly taught. And there's several conferences that are designed to make sense of it all. And here we have a major clash. We're in the big Solvay conference of 1927, and these are some of the leading scientists, with obviously Max Planck on the front, second from the left, Madame Curie right next to Planck. We have Albert Einstein in the front. And then on the backhand right side, you have people like, you have Heisenberg, you have Wolfgang Pauli to his right, Niels Bohr is there, Louis de Broglie, you see him in the middle. So you basically have weeks and weeks of clashing over which paradigm is going to be used as the standard scientifically accepted pathway to make sense of physical space-time. Obviously, the people who had created the fathers of this new physics and mother are people like Madame Curie, like Max Planck, like Albert Einstein, who did the pioneering work interpreting the photoelectric effect with helping Planck in enormous ways. So these people who are creating the paradigm shifting discoveries were very bothered by the fact that these new kids who were only trained in mathematics around Niels Bohr were all saying, no, the key is that if it behaves as a particle and it behaves as a wave, you just have to accept that it has two identities that have two different natures, and that's just the way they are. And if you can't predict where it's going to be, because if you try to measure a photon of light or an electron, if you try to measure it, that requires that another photon hit it and jump back to your eye, so that or your measuring device, right, in order for you to measure where it is and what speed it's in. And you can't do that. Every time you do it, you destroy the trajectory or the speed of the thing you're trying to measure. And so that was causing a problem. There couldn't be the satisfying sort of direct experience that we were formerly getting from measuring things like planetary motions. It didn't all of a sudden work on things that were that small. So again, these mathematicians were saying, well, the only solution is that there is no solution, that all we could know is probably where it might be. So it became a science of probably. We could take statistical analysis and say it's most likely going to be in this location over this location, but we can't ever really know. We can't know the principles because there are no principles. And so, you know, people who believed in principles, like, again, Max Planck and Einstein and Curie, had a big problem with that. And they were the ones who became known as the old crazy people who didn't want to accept the new science of the standard model, the people who gave birth to today's standard model of quantum mechanics or cosmology. It's really located in Niels Bohr, because these are all followers of Niels Bohr. Last two slides. So Niels Bohr is a guy who, I think he was a good guy in many ways. However, he was devoutly anti-causality, devoutly, coming out of Denmark. And the Copenhagen school was sort of, like I said, he created the original models of the electron. None of these guys really made discoveries. They liked modeling things. That was really what they did. He made a point in his Light and Life, the same year that Max Planck writes, Where is Science Going? Niels Bohr, who's now been declared the undisputed winner, and now all of science and science funding is going to follow their path and not Planck or Einstein. But he writes, indeed, the spatial continuity of our picture of light propagation and the atomicity of the light effects are complementary aspects in the sense that they account for equally important features of the light phenomenon which can never be brought into direct contradiction with one another, since their closer analysis in mechanical terms demands mutually exclusive experimental arrangements. At the same time, this very situation forces us to renounce a complete causal account of the light phenomenon and to be content with probability laws based on the fact that the electromagnetic description of energy transfer remains valid in a statistical sense. So basically, again, in short, we have to accept that all we have are statistical probabilities to work with. Nothing more causal can be expected. He goes on in the same Light and Life text saying, the straightforward solution of the unexpected paradoxes met with the application of our simplest concepts to atomic phenomenon might help us to clarify conceptual difficulties in other domains of experience. And so again, the thing that's happening here is he's saying the acausality, the absence of causality in this domain, this new domain of physics, we can now apply to every other domain of experience, whether biology, whether psychology, whether art theory. He had theories of art, philosophy, you name it. We can now develop a unified science that unites all of these different branches of human experience and science around a non-causal explanatory model. So that's what unites them, is that there is no reason or cause that's intelligible defining everything else. So now we can build up and have, science. And also this has application to statecraft, political science, economics. All of these things matter. And you can't understand George Soros's mind with his Institute for New Economic Thinking and his influence by Karl Popper and Open Society if you don't understand this grouping, this thinking, because this became, again, hegemonic. The last thing I want to just read, because we started with Kepler. I'm going to do a stop share. I'm going to try to, okay, I'm going to accept the idea that my camera is permanently off. That's okay. I want to just share one quote by Max Planck, and then we can read his essay. Okay, can people see that? Anybody?
Yeah.
Okay, you guys see that it says Max Planck on Johannes Kepler?
Yes, we can see that.
Okay, so this is from the end of Where is Science Going, as a Socratic dialogue between Planck, Einstein, and a science journalist named James Murphy.
Okay.
Cynthia, can you say something just to make sure I can hear you?
Hear me now?
Yeah, okay, that's good.
Okay. You want me to start?
Yes, Murphy.
Do you think that science in this particular might be a substitute for religion?
Not to a skeptical state of mind, for science demands also the believing spirit. Anybody who has been seriously engaged in scientific work of any kind realizes that over the entrance to the gates of the temple of science are written the words, "Ye must have faith." It is a quality which the scientists cannot dispense with. The man who handles a bulk of results obtained from an experimental process must have an imaginative picture of the law that he is pursuing. He must embody this in an imaginary hypothesis. The reasoning faculties alone will not help him forward a step, for no order can emerge from that chaos of elements unless there is the constructive quality of mind, which builds up the order by a process of elimination and choice. Again and again, the imaginary plan on which one attempts to build up that order breaks down, and then we must try another. This imaginative vision and faith in the ultimate success are indispensable. The pure rationalist has no place here.
How far is being verified in the lives of great scientists? Take the case of Kepler, whose 300th anniversary we were celebrating. You remember that evening when Einstein gave his lecture at the Academy of Science. Wasn't there something about Kepler having made certain discoveries, not because he set out after them with his constructive imagination, but rather because he was concerned about the dimensions of wine barrels and was wondering which shapes would be the most economic containers?
These stories circulate in regard to nearly everybody whose name is before the public. As a matter of fact, Kepler is a magnificent example of what I have been saying. He was always hard up. He had to suffer disillusion after disillusion, and even had to beg for the payment of the arrears of his salary by the Reichstag in Regensburg. He had to undergo the agony of having to defend his own mother against a public indictment of witchcraft. But one can realize, in studying his life, that what rendered him so energetic and tireless and productive was the profound faith he had in his own science, not the belief that he could eventually arrive at an arithmetical synthesis of his astronomical observations, but rather the profound faith in the existence of a definite plan behind the whole of creation. It was because he believed in that plan that his labor was felt by him to be worthwhile, and also in this way, by never allowing his faith to flag, his work enlivened and enlightened his dreary life. Compare him with Tycho de Brahe. Brahe had the same material under his hands as Kepler, and even better opportunities, but he remained only a researcher because he did not have the same faith in the existence of the eternal laws of creation. Brahe remained only a researcher, but Kepler was the creator of the new astronomy.
Beautiful.
Is that that's not a real dialogue.
That's a real dialogue. Yeah, that's the appendix of Where's Science Going? Yeah, and Einstein also takes part in this dialogue too. It's super nice. So I think with that, that sets the tone really nicely for Planck's battle, which we're about to read in the Philosophy of Physics, which anybody can access in the description box below this video. Okay. You guys can see that?
Yep.
Yes.
Okay. So we're going to go between page 9 to 43 today. It's going to be, I think, a relatively easy read compared to the stuff we have been working on over the past weeks. If people do want to stop or say a word or two, feel free to do so. Who wants to be, I guess, the first person could read, I don't know, 12 pages, then we'll just keep switching readers. Who would like to be? Oh, and some of the pages repeat. I'll just be wary on that. So who wants to read page 9? Physics and World Philosophy.
Yeah, I can start.
Okay.
Okay. Physics and World Philosophy. The subject of this chapter is the connection between physics and the endeavor to attain a general philosophy of the world. And it may well be asked wherein this connection consists. Physics, it may be urged, is solely concerned with the objects and events of inanimate nature, while a general philosophy, if it is to be at all satisfactory, must embrace the whole of physical and intellectual life, and must deal with questions of the soul, including the highest problems of ethics. At first sight, this objection may seem convincing, yet it will not bear closer investigation. In the first place, inanimate nature is, after all, part of the world, so that any philosophy of the world claiming to be truly comprehensive must take notice of the laws of inanimate nature. And in the long run, such a philosophy becomes untenable if it conflicts with inanimate nature. I need not here refer to the considerable number of religious dogmas to which physical science has dealt a fatal blow. The influence of physics upon a general world philosophy is not, however, confined to such a negative or merely destructive activity. Its contribution in a positive sense is of much greater importance. This is true with regard both to form and to content. It is common knowledge that the methods of physical science have proved so fruitful largely on account of their exactness, and have on this account provided a model for not strictly scientific studies. While in regard to content, it should be said that every science has its roots in life, and that similarly, physics can never be completely separated from its student. Every student, after all, is a personality equipped with a set of intellectual and ethical properties. Hence, the general philosophy of the student will always have some influence on his scientific work, while conversely, the results of his studies cannot but exert some influence on his general philosophy. It will be the chief purpose of the present chapter to demonstrate this in detail with respect to physics. I propose to begin with a general consideration. Any scientific treatment of a given material demands the introduction of a certain order into the material dealt with. The introduction of order and of comparison is essential if the available and steadily increasing matter is to be grasped, and the obtaining of such a grasp is essential if the problems are to be formulated and pursued. Order, however, demands classification, and to this extent, any given science is faced by the problem of classifying the available material according to some principle. The question then arises, what is to be this principle? Its discovery is not only the first, but, as ample experience proves, frequently the decisive step in the development of any given science. It is important at this point to state that there is no one definite principle available a priori and enabling a classification suitable for every purpose to be made. This applies equally to every science. Hence, it is impossible in this connection to assert that any science possesses a structure evolving from its own nature, inevitably, and apart from any arbitrary presupposition. It is important that this fact should be clearly grasped. It is of a fundamental significance because it demonstrates that it is essential, if there is to be any scientific knowledge, to determine the principle in accordance with which its studies are to be pursued. This determination cannot be made merely in accordance with practical consideration. Questions of value also play their part.
Okay. Everyone has a clear idea of the problem that he's defining here about the nature of science and how no principle can be discovered a priori. I like that. So has everyone heard the term a priori before? Okay. So yeah, there's no pre-existent just law that exists that you can just jump to and assume to be true without proving it reasonably to be true, upon which you're going to use as a principle to organize all of your data, all of the complex array of, evidence that you're going to be bringing into your science. So what are you judging it against when you're inputting and creating a science? And how do you remove that judgment from the values of the scientist, right? The personality, the subjective personality and values of the person thinking about the data and about their science. You can't. it's a part of the equation. So don't assume that there's a bridge between the observer and the observed, or, so.
Okay. Let us take a simple example from the most mature and exact of all sciences, mathematics. Mathematics deals with the magnitude of numbers. In order to obtain a survey of all numbers, the obvious method would be to classify them by magnitude, in which case any two numbers are close to each other in proportion as the difference between them is small. Let us take two numbers which are practically equal in magnitude, one of them being the square root of 2 and the other 1.414213562237. The former figure is a few billionths greater than the latter, and in every numerical calculation in physics or in astronomy, the two numbers can be treated as completely identical. So soon, however, as numbers are classified in accordance with their origin and not in accordance with their magnitude, a fundamental difference between the two numbers arises. The decimal fraction is a rational number and can be expressed by the ratio between two integers, while the square root is irrational and cannot be so expressed. If now it is asked whether these two numbers are closely related to each other or not, then any dispute on this question formulated in this manner would have no more meaning than a dispute between two persons facing each other and debating which side was right and which left. I have taken this simple example because I am convinced that many scientific controversies, and among them many which aroused a maximum of bitterness, have ultimately been due to the fact that the two opponents were, without clearly stating it, employing different principles of classification in the arrangement of their arguments. Every kind of classification is inevitably vitiated by a certain element of caprice and hence of one-sidedness. The selection of the principle of classification is even more important in the natural sciences. As an example, one might take botany. Some kind of nomenclature is essential, and hence all plants must be divided according to species, genera, families, etc. But according as different principles of classification were selected, so different systems evolved. In the history of botany, there have sometimes been sharp controversies between these systems, none of which can claim infallibility since each is affected by subjective bias. The natural system of plants now in general use, although superior to the earlier artificial systems, is not definitive nor clearly determined in every detail, but is subject to certain fluctuations corresponding to different attitudes taken by leading investigators to the question of the most expedient principle of classification. The necessity of introducing some classification and the caprice attaching to it is most striking and significant, however, in the non-scientific studies, and especially in history. Whether history is classified vertically or horizontally, whether it is arranged according to political, ethnographic, linguistic, social, or economic principles, the necessity continually arises of making distinctions which are seen on close consideration to be fluid and inadequate for the simple reason that any kind of classification inevitably separates cognate subjects and sunders closely allied matters. Thus, every science contains an element of caprice and hence of transitoriness in its very structure, a defect which cannot be eradicated because it is rooted in the nature of the case. In turning to physics, we are now faced by the task of classifying under various groups the events which we study.
Sorry, just quickly, is everyone following the general strain of thought? Yeah?
Mm-hmm.
Yes.
Okay. All right, cool.
This much is a preliminary demand. Now, all physical experiences are based upon our sense perceptions, and accordingly, the first and obvious system of classification was in accordance with our senses. Physics was divided into mechanics, acoustics, optics, and heat. These were treated as distinct subjects. In course of time, however, it was seen that there was a close connection between these various subjects, and that it was much easier to establish exact physical laws if the senses are ignored, and attention is concentrated on the events outside the senses. If, for example, the sound waves emanating from a sounding body are dealt with apart from the ear, and the rays of light emanating from a glowing body apart from the eye. This leads to a different classification of physics, certain parts of which are rearranged, while the organs of sense recede into the background. According to this principle, the heat rays emanating from a hot stove ceased to be the province of heat and were assigned to optics, where they were dealt with as though entirely similar to light waves. Admittedly, such a rearrangement, neglecting as it does the perceptions of the senses, contains an element of bias and arbitrariness. Goethe, who always insisted on the primary of the senses, would have been horrified by such an arrangement, for Goethe always concentrated on the event in its totality, insisted on the superiority of the immediate sensation, and hence would never have agreed to a distinction between the organ of sight and the source of light. If the eye were not of the nature of the sun, how could we see the light? Yet, it may be presumed that, had he lived a century later, Goethe would not have objected to the soothing light of an electric bulb on his desk, although its invention was made possible only by the particular physical theory which he had so vigorously opposed. Neither Goethe nor his great adversary Newton could have suspected while alive that this successful theory, when consistently developed, was doomed to give way to the opposite one-sidedness. I do not wish to anticipate, however, and now revert to a description of the further development of physics. Once these specific perceptions of the senses as fundamental concepts of physics had been eliminated from that science, it was a logical step to substitute suitable measuring instruments for the organs of sense. The eye gave way to the photographic film, the ear to the vibrating membrane, and the skin to the thermometer. The introduction of self-registering apparatus further eliminated subjective sources of error. The essential characteristic of this development, however, did not consist in the introduction of new measuring instruments of steadily growing sensitiveness and exactitude. The essential point was that the assumption that measurement gave immediate information about the nature of a physical event, whence it followed that the events were independent of the instruments used for measuring them, now became the foundation of the theory of physics. On this assumption, a distinction must be made whenever a physical measurement takes place between the objective and actual event, which takes place completely independently, and the process of measuring, which is occasioned by the event and renders it perceptible. Physics deals with the actual events, and its object is to discover the laws which these events obey.
Anyone should be okay with stopping if they want to and ask a question if they need to or want to clarify something. Is it so far okay?
Yes, I would just like to make a point.
Yeah, sure, John.
Having read ahead already, it seems to me that he's putting out the position of his team. You know, we said that was Einstein and Curie and Planck versus Bohr and his other team. But it seems to me that he's laying out a position, but giving himself some room that he could eventually meet the other team in the middle.
Yeah, he's trying to get rid of these polarizations that he sees between the radical empiricists who can't find any universals, you know, of the Copenhagen school, who in a sense they just see empirically, I can't grab anything empirically with direct perception, and thus they jump to their radical conclusions that there is thus no truth, versus those who just want to have their ivory tower formulas dictate what truth is, despite the fact that their senses might be showing them something totally opposite. And that's wrong too. And he's, trying to get across that this is a false polarization. You're framing the question improperly. And I like that example of the square root of 2 versus 1.4142. They seem equivalent. We're often told that they're equivalent, but they're really not. And when you look at their origins, you discover the difference, the hierarchy, that nobody could come to the discovery of 1.41 blah, blah, blah first. They had to first discover square root of 2 when they were doing work on doubling the surface area of a square. You quickly discover that there's this diagonal called the square root of 2. You could label it. And then you could discover, okay, if I try to express it in this one-dimensional non-area way, mathematically, I could choose to try to describe it in that infinite way, right? That will go on 1.41, and I'll always find another number. But they're not the same thing.
Yes, but I think that because right near that section, he lays out the point that this organization, the organizations that science lays down are basically, in some cases, somewhat arbitrary. I think he might have even gone on to say that that difference between the square root versus the decimal value would be a distinction without a difference.
Well, he's actually, I mean, we'll keep reading, and he's going to like revisit this as you've noticed in a variety of pathways. But I think he's really getting at the assumptions that people have that there is no. They think that they're talking the same language, but they're not. So you have these arguments that are going to be going on forever because two people are using different ideas of causality, of the nature of number of magnitude. And so that's not being, he's like, we have to resolve these fundamental assumptions first before we even have this debate. But yeah, you're totally right. He's trying to definitely find some middle ground that's not either extreme, but that has elements, better elements of both approaches without their limitations.
Or maybe
does somebody else want to kick in as far as reading or a question? Cody, you want to read a bit?
Yeah, I can read. Where did we leave off?
Page 17. where it's this method of interrogation, this method of interrogating nature?
This method of interrogating nature has been justified in the past by the wealth of results obtained by classical physics. For classical physics followed the methods indicated by this view, and results applied in practical life to applied science and to kindred pursuits are familiar and visible to all. A detailed description is hence unnecessary. Encouraged by this success, physicists proceeded on the road which they had entered. They continued to apply the principle of divide et impera. After the actual events had been separated from the measuring instruments, bodies were divided up into molecules, molecules into atoms, and atoms into protons and electrons. Simultaneously, space and time were divided into infinitely small intervals. Everywhere rigorous laws were sought and found as the process of subdivision went on. So the laws assumed simpler forms, and there seemed to be no reason for not assuming that it might prove possible to reduce the laws of the physical macrocosm to the same spatial temporal differential equations which are valid for the microcosm. These equations would then give for any given initial state of nature the reoccurring changes, and hence by integration the states for all future time, a view of the physical events of the world as comprehensive as it was satisfactory by reason of its harmony. The surprise was all the more striking and unpleasant when, at the beginning of the present century, the increasing delicacy and number of available methods of measurement showed, first in the field of heat radiation, later in that of light rays, and finally in that of electromagnetics or mechanics, that the classical theory as described above is faced by an insurmountable barrier. It may be best to give an example in order to calculate the movement of an electron. Classical physics must assume that its state is known, and this state embraces its position and velocity. Now it has found that every method permitting of an exact measurement of the electron's position prohibits an exact measurement of its velocity. And it was further found that the inaccuracy of the latter measurement varies inversely with the accuracy of the former, and vice versa. The phenomenon being governed by a law which is inaccurately defined by the magnitude of Planck's quantum. If the position of the electron is known exactly, its velocity is not known at all, and vice versa. Clearly, in these circumstances, the differential equations of classical physics lose their fundamental importance. And for the time being, the task of discovering in all their details the laws underlying the real physical processes must be regarded as insoluble. But of course, it would be incorrect to infer that no such laws exist. The failure to discover a law will, on the contrary, have to be attributed to an inadequate formulation of the problem and consequently inaccurate posing of the question. The question now is wherein the mistake consists and how can it be removed? It should be stressed first that it would be incorrect to speak of a breakdown of theoretical physics in the sense that everything achieved hitherto must be regarded as incorrect and must hence be rejected. The successes attained by classical physics are far too important to permit such drastic action. It is not the case that a new structure has to be erected, but that an old theory must be extended and elaborated. This being true, especially with the reprocess of subdivision went on. So
hold on. I think there's this, yeah, there's a repeat of the pages, sorry, with regards to
microphysics in the field of macrophysics, which deals with relatively large bodies of time. and the classical theory which always retain its importance. Clearly then, the mistake does not
Lie.
lie in the fundamentals of the theory, but in the face that among the assumptions used for the building it up, there must be one to which the failure is due, the elimination of which would allow the theory to be further extended. Let us consider the facts of reality. Theoretical physics is based on the assumption that there exists real events not depending upon our senses. This assumption must be in all circumstances be maintained, and even physicists and positivists learnings make use of it.
Oh no, and even physicists of positivist leanings make use of it. A
Yeah.
positivist is just somebody who believes only in radical sense perception, and not like the laws that are inaccessible to our senses. They deny that.
So they would reject theoretical physics because you cannot feel it. Is that what you're saying?
But he's making the point that they're not consistent with themselves because they make use of it. They can't be physicists if they don't make use of it, but they completely deny anything that smells of metaphysics. So anything that smells of anything like that might relate to principle, harmony, like these words are not something you can measure, cut, divide. They're transcendental concepts. So they just reject metaphysics as a religious basis almost, but they can't avoid using the language and the assumptions of metaphysics just to get by as human beings. So he's just taking a little pot shot at them.
Even if this school maintains that the priority of the sense data is the sole foundation of physics, it is yet compelled, in order to escape an irrational solipsism, to assume that there are such things as individual deceptions of the senses and hallucinations. And these can be eliminated only on the assumption that the physical observations can be reproduced at will. This, however, implies what is not evident a priori, namely that the functional relationships between sense data contain certain elements not depending upon the observer's personality nor upon time and place of observation. It is precisely these elements which we describe as the real part of the physical event and of which we attempt to discover the laws. We saw above that classical physics, beside assuming the existence of real events, has always further assumed the possibility of obtaining a complete grasp of the laws governing the real events. The method of obtaining this grasp being a progressive, spatial, and temporal subdivision of the direction of the infinitely small. More closely considered, this assumption must be largely modified, since it leads, example, to the conclusion that the laws governing a real event can be completely understood if it is separated from the event by which it is measured. Now, evidently, the process of measuring can inform us about the real event only if there is some kind of causal connection between the two.
Causal.
Causal.
Yeah.
Yes, causal. Causal connection between the two. And if there is such a connection, then the process of measuring it will, in some degree, influence and disturb the event, with the consequence that the result measurement is falsified. This falsification and consequent error will be great in proportion as the causal nexus between the real objective and the measuring instrument is close and delicate. It will be possible to reduce it by relaxing the causal nexus, or to express it differently, by increasing the causal distance between the object and the measuring instrument. It is never possible to eliminate the interference altogether, since if the causal distance is assumed to be infinitely great, i.e., if we completely sever the object from the measuring instrument, we learn nothing at all about the real event. Now, the measuring of single atoms and electrons require extremely delicate and sensitive methods, and hence implies a close causal nexus. The exact determination of the position of an electron therefore implies a relatively powerful interference with its motion. And conversely, the exact measurement of its velocity of an electron requires a relatively lengthy time. In the first case, there is interference with the electron's velocity. In the second, its position in space becomes indefinite. This is the causal explanation of the inaccuracy described above. Convincing as these considerations may appear, they do not reach the core of the problem. The fact that a physical event is interfered with by the measuring instrument is familiar in classical physics, and at first, it is not apparent why increasing improvements in methods of measuring should not permit us to ultimately to calculate in advance the amount of interference when dealing with electrons. If, therefore, we wish to understand the failure of classical physics in the microcosm, we must carry our investigations somewhat deeper.
Yeah, I mean, that's pretty obvious, right? Like in classical physics, because he's currently addressing his thoughts to the classical physicists who, quantum mechanics, the statisticians are all saying, because we cannot know absolute truth in a mathematically certain absolute way, there is none. And he's saying, well, let's define what is science, and there has been progress, but what is it, and where does it lack? And like, if you try to measure a sound wave, you have to have, an instrumentation. Imagine like the 19th century, how were they measuring sound waves, or like the radiation even being emitted by uranium? Well, they had to have like gold leafs set up floating between each other inside of a glass, casing. And depending upon the intensity of the radiation of whatever substance you were trying to measure, it would cause it would cause the gold foils to pull together, either by ionizing the air between the gold foils. So depending on the speed at which the gold foils would close in on themselves would give you a sense of the intensity of the radiation from whether it was thorium or radium or something else. But that itself is influencing, the radiation itself is influencing the gold foils. It's not giving you, and all of the things you've set up are also influencing the radium and the rate of emissions. So you're not dealing with it in a perfect, abstract sense. You're setting up an experiment which is influencing the thing you're experimenting upon as well. So it's giving you good data, but the data is intrinsically flawed by the nature of it. So you're always trying to minimize the flaws, but you're not assuming that the data is the truth. It's just you're using it as a useful thing to zero in on truth, which is something other than the data. Sorry, I just wanted to chime in with that.
All good. The study of this question was carried forward considerably by the establishment of quantum mechanics or wave mechanics, from whose equations observable atomic processes can be calculated in advance. As the rules are observed and results of such calculations agree exactly with the experience, it is true that unlike classical mechanics, quantum mechanics does not give the position of an individual electron at any given time. What it does is to state the probability that an electron will be at any given that it will be at any given place at any given time, or alternatively, given a multitude of electrons, it states the number which any given time will be at a given place. This is a law of purely statistical character. The fact that has been conserved by all the measurements hitherto made, and the further fact that there is such a thing as the uncertainty relation, has induced certain physicists to conclude that statistical laws are the only valid foundations of every physical law, more particularly in the field of atomic physics. and to declare that any question about the causality of individual events is physically meaningless. We here reach a point whose discussion is of particular importance, since it leads us to a fundamental question. What is the task and what are the achievements of physics? If we hold that the object of physics is to discover the laws governing the relationship between real events of nature, then causality becomes a part of physics, and its deliberate elimination must give rise to certain misgivings. It should first be observed that the validity of statistical laws is entirely compatible with a strict causality. Classical physics contains numerous examples. Thus, we must explain the pressure of a gas on the wall of the containing vessel as due to the irregular impingement of numerous gas molecules flying about in all directions. But this explanation is compatible with the admission that the impingement of any one molecule upon another or upon the wall is governed by law and hence is completely determined causally. It may be objected that a strict causality can be regarded as definitively proved only if we are in a position to predict the entire course of the event. And it might be added that nobody can check the movement of any single molecule. To this, we might reply that a rigorously exact prediction is never possible of any natural event, so that the validity of the law of causality can never be demonstrated by an immediate and exact experiment, since every measurement, however exact, inevitably involves certain errors of observation. Yet, in spite of this result of the measurement, as well as individual errors of observation, are attributed to definite causes. When we watch the waves breaking on the seashore, we have every right to feel convinced that the movement of every bubble is due to a strict causal law, although we can never hope to follow its rise and fall, still less to calculate it in advance. It is at this point that the uncertainty relation is brought forward. While classical physics has fashioned, it might be hoped that the inevitable errors of observation could be reduced beneath any given limit by an appropriate increase in the accuracy of measurements. This hope was destroyed by the discovery of Planck's quantum, since the latter implies a fixed objective limitation of the exactitude which can be reached, within which limit there is no causality, but only doubt and contingency. We have already prepared a reply to this objection. The reason why the measurements of atomic physics are inexact need not necessarily be looked for in any failure of causality. It may equally well consist in the formulation of faulty concepts and hence of inappropriate questions.
I really just love that example he gave a couple of paragraphs earlier, by the way. I just want to chime in how much I appreciated that, because I encountered that so much. I've had so many people in discussions where I would get people who said, well, because you can't know where, that exact same thing, where you can't know where every molecule is going to be in an ocean, thus what seems like order of the currents is actually just an illusion governed by chaos. This is a big thing. People actually believe that. But it's like, they're completely, it's like trying to analyze a Rembrandt painting with your eyeball like 2 millimeters from the surface. You know, you'll never be able to see the whole. You're just so stuck on these individual little pieces of bark on a tree. So the whole doesn't even exist to you. You can't, they lose their ability to think about a whole concept.
Yeah.
Sorry.
It is precisely the reciprocal influence between the measurement and the real event which enabled us to understand the uncertainty relation, at least to a certain degree. According to this view, we can no more follow the movement of the individual electron than we can see a colored picture whose, is there more?
Okay, let me just fix that.
Whose dimensions are smaller than the wavelength of its color. It is true that we must reject as meaningless the hope that it might eventually prove possible indefinitely to reduce the inaccuracy of physical measurements by improving the instrument. Yet the existence of an objective limit like Planck's quantum is a sure indication that a certain novel law is at work, which has certainly nothing to do with statistics. Like Planck's quantum, every other elementary constant, e.g., the charge or mass of an electron, is a definite real magnitude. And it seems wholly absurd to attribute a certain fundamental inexactitude to these universal constants, as those who deny causality would have to do as they wish to remain consistent. The fact that there is a limit to the accuracy of the measurements in atomic physics becomes further intelligible if we consider that the instruments themselves consist of atoms and that the accuracy of any measuring instrument is limited by its own sensitiveness. A weighbridge cannot weigh to the nearest milligram. Now, what can we do if the best that we have is a weighbridge and there is no hope of obtaining anything more accurate? Would it not be better to give up hope of obtaining exact weights and to declare the pursuit of the milligram to be meaningless, rather than to pursue a task which cannot be solved by direct measurement? This argument underestimates the importance of theory, for theory takes us beyond direct measurements in a way which cannot be foretold a priori. And it does so by means of the so-called intellectual experiments, which render us largely independent of the defects of the actual instruments. It is wholly absurd to maintain an intellectual experiment it is wholly absurd to maintain that an intellectual experiment is important only in proportion as it can be checked by measurement. For if this were so, there could be no exact geometrical proof. A line drawn on paper is not really a line, but a more or less narrow strip, and at a point, a larger or smaller spot. Yet nobody doubts the geometrical constructions yield a rigorous proof. The intellectual experiment carries the mind of the investigator beyond the world and beyond actual measuring instruments, and enables him to form hypotheses and to formulate questions which, when checked by actual experiment, enable him to perceive new laws even when these do not admit of direct measurement. An intellectual experiment is not tied down to any limits of accuracy, for thoughts are more suitable than atoms or electrons. More subtle.
Yes.
For thoughts are more subtle than atoms or electrons. Nor is there any danger that the event which is measured can be influenced by the measuring instrument. An intellectual experiment requires one condition only for its success, and this is the admission of the validity of any non-self-contradictory law governing the relations between the event under observation. We cannot hope to find what is assumed to be existent.
Okay, I think with that, let me just ask, did anybody have a question or fell off mute there? Does anybody have a thought or a question they'd like to throw in based on some of that dense reading? pretty good. Yeah, I like the idea of this geometrical, the idea of a thought experiment requires oftentimes that you have recourse to geometrical proofs, right? Whether it's the doubling of a square, the doubling of the volume of a cube, the cross sections, you know, if you want to generate an ellipse to be able to play around on a cone, an idealized cone, you can never actually see the perfect cone or the perfect cube in physical reality. If you try to make a cube or a square or a cone in physical reality, there will be subtle, even if you have like the best lasers that you're using to cut your, you know, your cone out of a material, the best laser printer, whatever, it's all being shaped by a certain curved space-time. And there will be subtle inconsistencies on a very low level, even if it's below the ability for us to measure them. So you can't get the idealized cone in physical world, but you can conceptualize it, right? And your ability to conceptualize that cone or that circle or that cube gives you the ability as a cause to generate it. If you didn't have that perfect idea in the mind, how would you possibly go about constructing it physically? You couldn't. So there's a relationship between this immaterial domain of geometrical proofs, where we access, you know, Plato's concepts of ideas, and the physical world. But there's this bridge as well. There's a gulf if you're trying to just like measure it materialistically, like what went into creating my cone, my physical plastic cone, and you measure all of the steps of cause before it, you know, putting the resin inside of the 3D printer and plugging in, using my, you know, the electric circuits that I'm plugging in to my computer to impose the data that's gonna like put the machine into motion. And I could just infinitely, constantly just go back one step mechanically, but I'll reach this gulf when I get to the realm of metaphysics, of the mind, of the thought, right, that put the idea into motion. So.
Well, I would like to add one thing to that point, and that is a couple of pages back, it seems to me he's not saying that because we cannot measure the subatomic particles, that they don't have a position or that they don't have a velocity.
Mm-hmm.
He's saying that they do, it's just that we're not able to measure it. And I think that kind of speaks to the next step, which is the thought experiment,
mm-hmm.
as a way to somehow deal with, you know, how would we measure it if we could?
John, that's wonderful. Thank you. Okay, that sets up, I think, the next phase of where he's going with this. Now, let's maybe shake up the reading a little bit. John or Kwan, one of you guys want to race to the page 28?
Sure, I'll take it.
Awesome.
Maybe not quite too long a chunk, because I think that some of the readers have been tiring towards the end.
Well, we're going to end on page, the first section ends on page, I think, 44. So that gives us 15 or 16 pages.
Okay, well, let's see how much we can do here.
Okay.
Let's see, I think the next thing to start with is the paragraph starting with admittedly, an intellectual experiment is an abstraction. Is that where we started?
Yes, sir.
Okay. Admittedly, an intellectual experiment is an abstraction. An abstraction, however, as essential to the experimenter and to the theorist as the abstract assumption that there is a real external world. Whenever we observe an event taking place in nature, we must assume that something is happening independently of the observer, and conversely, we must endeavor to eliminate as far as possible the defects of our senses and of our methods of measurement in order to grasp the details of the event with greater perfection. There's a kind of opposition between these two abstractions. While the real external world is the object, the ideal spirit which contemplates it is the subject. Neither can be logically demonstrated, and hence no reductio ad absurdum is possible if their existence is denied. The history of physics bears witness, however, that they have played a decisive part throughout its development. The choicest and most original minds, men like Kepler, Newton, Leibniz, and Faraday, were inspired by the belief in the reality of the external world and in the rule of a higher reason in and beyond it. It should never be forgotten that the most vital ideas in physics have this twofold origin. In the first instance, the form which these ideas take is due to the peculiar imagination of the individual scientist. In the course of time, however, they assume a more definite and independent form. It is true that there have always been in physics a number of erroneous ideas on which a quantity of labor was wasted. Yet on the other hand, many problems which were at first rejected as meaningless by keen critics were eventually seen to possess the highest significance. 50 years ago, positivists considered it meaningless to ask after the determination of the weight of a single atom, an illusory problem not admitting scientific treatment. Today, the weight of an atom can be stated to within its 10,000th part, although our most delicate scales are no more fit to weigh it than a weighbridge is to determine milligrams. One should therefore beware of declaring meaningless a problem whose solution is not immediately apparent. There is no criterion for deciding a priori whether any given problem in physics has a meaning or not, a point frequently overlooked by the positivists. The only means of judging a problem correctly consists in examining the conclusions to which it leads. Now, the assumption that there are rigid laws applicable to physics is of such fundamental importance that we should hesitate before we declare the question whether such laws are applicable to atomic physics to be a meaningless one. Our first endeavor, on the contrary, should be to trace out the problem of the applicability of laws in this field. Our first step should be to ask why classical physics fails in the question of causality, when the interference arising from the measuring instrument and the inadequate accuracy of the latter are both insufficient to explain this failure. Plainly, we are forced to adopt the obvious but radical assumption that the elementary concepts of classical physics cease to be applicable in atomic physics. Classical physics is based on the assumption that its laws are most clearly revealed in the infinitely small, for it assumes that the course of a physical event anywhere in the universe is completely determined by the state prevailing at this place and in its immediate vicinity. Hence, such physical magnitudes relating to the state of the physical event as position, velocity, intensity of the electric and magnetic field, etc., are of a purely local character, and the laws governing their relation can be completely expressed by spatial temporal differential equations between these magnitudes. Clearly, however, this will not suffice for atomic physics, so that the above concepts must be made more complete or more universal. In which direction, however, is this to be done? Some indication may perhaps be found in the recognition, which is daily spreading wider, that the spatial temporal differential equations do not suffice to exhaust the content of the events within a physical system, and that the liminal conditions must also be taken into consideration. This applies even to wave mechanics. Now, the field of the liminal conditions is always finite, and its immediate interference in the causal nexus is a new manner of looking at causality and one hitherto foreign to classical physics. The future will show whether progress is possible in this direction and how far it will lead. But whatever results it may ultimately reveal, it is certain that it will never enable us to grasp the real world in its totality any more than human intelligence will ever rise into the sphere of ideal spirit. These will always remain abstractions, which by their variation lie outside actuality. Nothing, however, forbids us to believe that we can progress steadily and without interruptions to this unattainable goal. And it's precisely the task of science, with its continual self-correction and self-improvement, to work in this direction without cease once it has been recognized as a hopeful direction. This progress will be a real one and not an aimless zigzag, as is proved by the fact that each new stage reached enables us to survey all the previous stages, while those which remain to be covered are still obscure. Just as a climber trying to reach higher altitudes looks down upon the distance he has covered in order to gain knowledge for the further ascent, a scientist is happy not in resting on his attainments, but in the steady acquisition of fresh knowledge. I have so far confined myself to physics, but it may be felt that what has been said has a wider application. Natural science and the intellectual sciences cannot be rigorously separated. They form a single interconnected system, and if they are to be touched at any part, the effects are felt through the ramification of the whole, the totality of which is forthwith set in motion. It would be absurd to assume that a fixed and certain law is predominant in physics, unless the same were true also in biology and psychology. We may perhaps here deal with free will. Our consciousness, which after all is the most immediate source of cognition, assures us that free will is supreme. Yet we are forced to ask whether human will is causally determined or not. Put in this way, the question, as I have frequently tried to show, is a good example of the kind of problem which I've described as illusory, by which I mean that taken literally, it has no exact meaning. In the present instance, the apparent difficulty is due to an incomplete formulation of the question. The actual facts may be briefly stated as follows. From the standpoint of an ideal and all-comprehensive spirit, human will, like every material and spiritual event, is completely determined causally. Looked at subjectively, however, the will, insofar as it looks to the future, is not causally determined because any cognition of the subject's will itself acts causally upon the will, so that any definitive cognition of a fixed causal nexus is out of the question. In other words, we might say that looked at from outside, objectively, the will is causally determined, and that looked at from inside, subjectively, it is free. There is here no contradiction, any more than there was in the previous debate about the right and left-hand side, and those who fail to agree to this overlook or forget the fact that the subject's will is never completely subordinate to its cognition, and indeed always has the last word.
Bam, I love that. That's so good.
I thought it was rather convoluted.
Oh, no, but when you think of examples concretely, like I know that if I felt, I desire revenge because somebody wronged me, as soon as I start thinking about my desire, but that very act changes my desire. I become a little bit ashamed that I had that feeling, like if I just reacted without self-reflection, without objectively looking at my subjective feeling, I would have possibly done something I would have regretted, as I have in the past. But as soon as you actually become self-reflective in that way, all of a sudden, yeah, you become both the observer and the observed, and you change what you're observing.
Well, what you just said points out that he needed to provide an example to better clarify that paragraph.
Yes. Well, it's a good habit. I've noticed that even in reading Plato as well, like they'll often generalize something. And I think these guys are sort of teasing you to, as a reader, be perplexed and think, is there an example to put meat on the bones of this generality, or is it just fluff? I think he's sort of teasing you a little bit to do it yourself. But
well, we can help.
Not. I mean, it would have been definitely appropriate if he had.
All right. I'll continue with a couple more pages.
Yeah.
In principle, therefore, we are compelled to give up the attempt to determine in advance the motives guiding our actions on purely causal lines, that is, by means of purely scientific cognition. In other words, there is no science and no intellect capable of answering the most important of all the questions facing us in our personal life. The question, that is, how we are to act. It might thus be inferred that science ceases to play a part as soon as ethical problems arise. Yet such an inference would be wrong. We saw above that in dealing with the structure of any science and in discussing its most suitable arrangements, a reciprocal interconnection between epistemological judgments and judgments of value was found to arise, and that no science can be wholly disengaged from the personality of the scientist. Modern physics has given us a clear indication pointing in the same direction. It has taught us that the nature of any system cannot be discovered by dividing it into its component parts and studying each part by itself, since such a method often implies the loss of important properties of the system. We must keep our attention fixed on the whole and on the interconnection between the parts. The same is true.
Just mental note for people. We're not going to give any examples right now, but think maybe take a note of this and think of examples of systems which, when you try to investigate them by breaking them up into parts, you lose what you were trying to investigate to begin with. Maybe we talk about that next week when we meet up again.
Okay. The same is true of our intellectual life. It is impossible to make a clear cut between science, religion, and art. The whole is never equal simply to the sum of its various parts. And this is true also of mankind. It would be folly to attempt to obtain an understanding of a mankind by studying a number of men, however great. For each individual belongs to some community, to a family, a clan, or a nation, a community of which he must form a part, to which he must subordinate himself, and from which he cannot sever himself with impunity. For this reason, every science, like every art and every religion, has grown up on a national foundation. It was the misfortune of the German people that this was forgotten for many years. Perhaps somebody else can finish this section.
I vote for Quan. Quan? You are on mute, Quan. Ah.
Sorry. Okay. It may be said that there is nothing new in this and that it can be acknowledged without the aid of physics. This is true, and all that I wish to show is that the position of physics, far from being unique, leads us to the same results and the same views as every other science. However, different may be the point from which it starts. The real strength of its position is, in fact, seen if our argument is further developed, for it is only then that its tendency can be most clearly seen, which is to disregard its immediate origin and to expand in every direction, like a healthily growing tree, which tends to grow into the air and to stretch its branches in every direction, though at the same time it remains firmly rooted in the soil. If science is unable or unwilling to extend beyond the limits of the nation, it is unworthy of the name of science. And in this connection, physics enjoys an advantage over other branches of science. Nobody will dispute that the laws of nature are the same in every country, so that physics is not compelled to establish its international validity, like history, where it has actually been asked whether an objective history can be an ideal to be aimed at. Ethics also is supranational. Otherwise, ethical relations could not exist between the members of different nations. Here again, physics takes up a strong position. Scientifically, it is based on the principle that it must contain no contradiction, which in terms of ethics implies honesty and truthfulness. And these qualities are valid for all civilized nations and for all time, so that scientific principle may claim to rank among the first and most important of virtues. I do not think that I exaggerate in saying that an infraction of this ethical demand is discovered and repudiated more quickly and certainly in physics than in any other science. It is rather shocking to notice the difference between such strictness and the thoughtless laxity with which faults are accepted in everyday life. I have not so much in mind the so-called conventional falsehoods, which in practice are harmless and to a certain extent, indispensable to daily intercourse. Conventional falsehoods do not deceive precisely because they are conventional. The harm begins when there is an intention to deceive the other party and to convey to him a faulty impression. It is the duty of those who work in responsible positions to reform this matter ruthlessly, as well as to set an example worth following. Justice is inseparable from truthfulness. Justice, after all, simply means the consistent application in practice of the ethical judgments which we pass on opinions and actions. The laws of nature remains fixed and unchanged, whether applied to great or to small phenomena. And similarly, the communal life of man requires equal right for all, for great and small, for rich and poor. All is not well with the state if doubts arise about the certainty of the law, if rank and family are respected in the courts, if defenseless persons feel that they are no longer protected from the rapacity of powerful neighbors, and if the law is openly wrenched on grounds of so-called expediency. The populace has a keen sense of the security of the law, and nothing rendered Frederick the Great more popular than the legend of the Miller of Sans Souci. Such principles made Germany and Prussia great. It is to be hoped that they will never be lost. And it is the duty of every patriot to work for their preservation and consolidation. At the same time, it must be understood that the goal at which we aim, a permanently satisfactory condition, can never be attained in its perfection. The best and maturest ethical principles must fail to take us to do an ideal perfection. They can never do more than indicate the direction in which we can look for our ideal. If these facts are disregarded, there is a danger that the seeker may despair altogether or may doubt the values of ethics, a state in which, especially if he is honest in his dealings with himself, he may easily end by attacking ethics. There are numerous examples of this among the philosophies of ethics. The case here is the same as in science. What is important is not to have a permanent possession, but to work unceasingly towards the ideal aim, to struggle daily and hourly towards a renewal of life, and despite every setback, to strive towards improvement and perfection. Yet in the end, we may be tempted to ask whether such an unceasing, though fundamentally hopeless struggle is not wholly unsatisfactory. It may be asked whether a philosophy has any value at all if its victories are left without a single fixed point, affording them a firm and immediate security in the continual perplexity and hurry of their existence. Fortunately, this question admits of an answer in the affirmative. There is a fixed point and a secure possession, which even the least of us can call his own at all times, and inalienable treasure which guarantees to thinking and feeling man their highest happiness, since it's assure their peace of mind, and thus has an eternal value. This possession is a pure mind and goodwill. These afford secure holding ground in the storms of life, and they are the primary condition underlying any really satisfactory conduct, as equally they are the best safeguard against the torture of remorse. They are the essential of every genuine science, and they are equally a sure standard by which to measure the ethical value of every individual. Those who are ever striving forward, them we can save. End of chapter.
End of chapter. Great. Good. We made it. Yeah, and I could just, I have a sense that sometime after, when we finish this essay, we'll definitely want to read some material by Plato that I could just see animating Planck's own thinking in several locations, including the Meno, the Gorgias, the Phaedo, where the example of somebody who naively gives their faith to a leader or to a set of beliefs, professing to be truthful, but that person doesn't have firm foundations, and they find that the faith that they gave was to a false deity or a false icon, and then they start just hating ethics. They hate ideas, or they become a misanthrope when that person that they trusted turns out to be a liar, because they didn't have firm foundations to begin with, you know. So there's just so many things, but yeah, this was good. This was very, very good, and I'm sure Nietzsche would not have been happy to have read this.
Wow. You know, the poor Nietzsche should have found a good master, but it was not in his fate. So
sadly not. He tried, but not hard enough.
yeah.
Cool. Any final thoughts before we kick off for the evening? Let it all just sink in. Okay. So next week we'll do part 3. I won't do an intro, obviously, so we'll be able to jump right into the reading much quicker, and we'll get done quicker too. This Sunday we have a class by Martin Seif, where he's going to look at some of the work by Hans Alfvén and some Russian scientists I've never heard of who did work on cosmology in the 30s. So anyway, that sounds to be interesting at 4 p.m. Sunday, and then we'll meet back on Wednesday, usual time, to continue section 2 of Max Planck.